Hi, everybody. Welcome back. Welcome back to the Building a Star on Earth, the Road to Fusion Energy YouTube series course. My name is John. I'm a PhD student at Columbia University's Plasma Physics Lab, or the Fusion Research Center. And today, for our second video, we're going to be talking about fusion as an energy source. Part one, there will be a part two to this video that will be the next video in this series. So, without further ado, let's get started. And as with last time, as I will continue to remind you, the number one thing to remember through this whole course is to ask questions, whether that's in the chat on this video, whether you're emailing us from the Columbia Plasma Physics website. Really, asking questions is the best way to learn. There's no such thing as a simple or stupid question especially in the realm of plasma physics and fusion. So I encourage you guys, ask questions. We'll do our best to get back to you guys and provide responses. So yeah, really engage with us, engage with this course. It's a great way to learn and take initiative with this information. All right, and with that, what are we going to talk about in this video? So we're going to do a quick review of what the previous video talked about, and that's talking about plasma and fusion. We defined what plasmas are, we defined the fusion process, and then in the new material, we're going to talk about why we need fusion. And then we're going to go on to talk about how fusion compares to other energy sources, clean and non-renewable energy sources. And then we're going to talk a bit about the history of fusion. And in part two of this course, we'll talk a lot more about how we measure fusion as like in terms of fusion power out and fusion performance metrics and where we are as a society and a research field in getting fusion onto the power grid. So with that, let's do a bit of review. So you might remember from the past video, the four states of matter. Indeed, there are solids, liquids, and gases. Solids have strong intermolecular forces. Liquids have slightly weaker intermolecular forces. Gases are pretty much unbound atoms without intermolecular forces that are flying around pretty much freely. And then you can get between these states by adding heat to each one. So just like you have a block of ice that is solid, you melt it, you add heat, you melt it. It's a liquid, it's water. You add more heat, you boil it, it's gas. You add more heat to that, and eventually you get a plasma where at very high temperatures, these gas particles can hit into each other and actually ionize or add enough energy to the electrons on these atoms and eject those. So you have pretty much a free-flying soup of charged particles, electrons, and newly positively charged nuclei. So that was a quick review of how we get to plasmas as the fourth state of matter. And you might also remember that plasmas, because they're made up of these freely floating charged particles, they have a lot of qualities that relate to electric and magnetic fields. In addition, they can respond to electric and magnetic fields as charged particles respond to electric and magnetic fields. This will actually be the topic of a lecture or a class in a few videos from this one. Again, plasmas are very hot. You need multiple thousands or tens of thousands of degrees Kelvin to actually even get to a plasma in many cases. So the ions and electrons are moving at high speeds. And oftentimes these plasmas are characterized by their visibly glowing characteristics, especially colder and some denser plasmas as well, as you have electrons and other charged particles that are flowing around and accelerating and releasing electromagnetic radiation as they decelerate, whether within bounds of an atom or just generally around in the plasma. So that's a quick review of what plasmas are. And now you might remember a bit about fusion, where we talked about the different forces in nature, and we talked about how when you have two charged particles, they might come close to each other and repel each other if they have the same charge. But when they come close enough, if you can get it beyond this electromagnetic force, this electromagnetic barrier, this Coulomb barrier we talked about last time, the strong force, which is a different fundamental force of the universe, will take over, and these two atoms will combine and they will fuse. And this is the fusion process. And in the example that we talked about with the fusion process, which is something we'll talk quite a bit more about in this video and the following video is deuterium and tritium fusion processes. And that is, if you remember, deuterium and tritium are hydrogen isotopes. They have different numbers of neutrons, but the same number of protons. And when we do a fusion process with deuterium and tritium, and we have these two elements fused, or these two atoms fused, we get out a alpha particle or a helium particle, which is two protons and two neutrons. Again, there are no electrons involved here. And then we get a neutron that comes out. And the helium particle has 20% of the energy and kinetic energy from this interaction. If you remember this mass difference that it comes from the total mass of the sum of the mass of the two reactants, the deuterium and tritium, being less than that of the helium and neutron, the products, because those masses are different, in order to conserve energy, thanks to E equals mc squared, we have to put the rest of the energy somewhere else, and that goes into the kinetic energy of the helium particle and the neutron. So the helium has 20% of this energy, this kinetic energy, which is 3.5 MeV, shown on the slide here. And the neutron has 80% of that energy, and that's 14.1 MeV. And that's actually what we use typically to generate the electricity coming out of these fusion processes, which we talked a bit about last time. The helium particles or the alpha particles are used to continue to heat the plasma and create more fusion. That concludes our quick review. And now we'll talk about why do we need fusion. Now, this section is going to be a little bit of a sidebar, I'd say, relative to the conversation about the development of fusion, but I think it is a very important conversation to have because it really motivates a lot of the reason behind why we need to do fusion and why we need to adopt fusion as an energy source in our society. And before I give this talk, I will say as well, this is going to be a purely technical conversation. This topic has a lot of political analogies and political conversations around it as well. However, and political and social and economic conversations as well. The economic stuff is important to us. However, this is a technical video series. I will be presenting technical information to you. I will try to avoid the political conversation as much as possible in order to just talk about like what we see as scientists in the realm of climate change and in the realm of energy sources as well. So I will do my best there, and we can start talking about this. So as we, increase our population as a human society, and we increase our computing power, we increase our research power in different household items and transportation methods, we increase our energy demands. And therefore, we are going to use more and more fossil fuels or more and more non-renewable energies to create the energy that we need to function as a society. We start creating these side effects of climate change and pollution, and that has other side effects of mass migrations, extinctions, weather events, health effects. In addition, there's also a conversation to be had about making electricity more accessible to all parts of the world as well, and not just first world countries. And all of this kind of, maybe we won't talk in specifics about that last point, but there's a lot of evidence behind what is creating the climate change scene. And that's what I'm going to talk about in the next few slides. So the energy sources that make up most of our energy production, they center around fossil fuels that create greenhouse gases that are causing this warming of the earth. So in addition, these non-renewable energy sources tend to be the ones that are contributing to these greenhouse gases, but they are also non-renewable, meaning that we will run out of them at some point. So a sustainable world where we can continue and not damage the world around us and continue to live as a human society is one that's net zero for carbon. So we don't produce more carbon we don't add more carbon to the atmosphere than is already in it naturally. And Fusion is a clean energy source and it is a renewable energy source as well. And we'll talk about, so it doesn't emit any carbon or fossil fuels or anything. And it also is the most efficient amount of energy per like unit mass and time that we can actually make. And I'll give the specific numbers to this as well. And indeed, if we make our world all based off of fusion, it will undoubtedly look like this green picture on the screen. So let's get into the specifics. So this is a graph that I think is very interesting. I think it's this is not, again, this is like a purely technical information graph. This is a global mean temperature difference from some like standard mean value over the past 150 or so years, taken by 6 different independent either satellite data or different probes, basically. I'm actually not sure the exact probe method of each one of these, but you can read more about it in the report that is linked. And each one of these probes, independently, you can see the results kind of converge on the same line as you get towards better data in modern society. All of these probes have us just increasing the temperature, the global mean temperature of the world, compared to the 1850 to 1900 average. So this is just like this is just something that's happening, and we're observing that it's happening. And you might ask why. So it is interesting to have the discussion about carbon in the atmosphere at the same time. And I think that this figure is very informative about what is happening with the carbon in the atmosphere and why we see an increasing amount of carbon in the atmosphere. There are many plots in this report, in the United Nations report that is being referenced here, and also just all around the internet, as we also see a super rise in carbon in the atmosphere. And I believe I will show a plot of that in a few slides as well. However, we are experiencing this because we generate fossil fuels and we generate carbon from fossil fuels, from things that we do as humans, and that's on the left side of this figure, and that gives us a total emissions of 40.2 with some unit on it. I think the unit isn't really important here; it's more the comparison. There's also a growth rate that's due to the atmosphere, and that's a different effect that I won't talk about. But the planet also has sinks of carbon dioxide, and of fossil fuels, so it takes carbon out of the atmosphere naturally, thanks to the oceans and thanks to the lands. However, we're exceeding the amount that is being taken out of the air by the ocean and the land. Therefore, we're just adding more. And even though the Earth has these feedback cycles, we're adding more and more and accumulating more carbon into the world and into the atmosphere. And that's in addition to these rising temperatures. So it's interesting that these two things are happening simultaneously. There is the breakdown of where these fossil fuels are coming from is very interesting in the argument for fusion and for replacing fossil fuels that are powering the grid itself. Because so if you look at this plot, this pie chart, residential and commercial come from fossil fuels that are powering the grid. Industry is also mostly coming from fossil fuels powering the grid. Agriculture is really fossil fuels that are coming from like livestock and stuff. So that's not included here. Transportation is fossil fuels that might not necessarily be burned for grid power. And grid power is like when you plug your phone into the wall, like you're pulling power from the grid. Whereas like your car burning fossil fuels directly is not burning power from the grid. However, eventually, if we move, which we probably will, to electric cars and all electric vehicles, those will then be pulling power from the grid, which may still be fossil fuels if that's what's powering the grid. So fusion would be an energy source that would power the grid, and that would take away, if we have like an electric car or electric transportation society, that would take away 90% of the fossil fuels that are being emitted. So this is like one of the arguments for fusion, and for renewable and new energy sources that directly replace fossil fuels that power the grid. And now let's talk about a little bit more about climate change. So we talked a bit about the temperature rising. We talked a bit about the carbon, which we'll talk a bit more about in a second, about why we know that there's a connection between increased carbon in the atmosphere and temperatures. But we also should talk a bit about the effects of the changing climate. So we know that there's this temperature that's increasing. What is happening? Is it just going to get a little bit warmer, or are there going to be some other things that are happening? So you may have heard of sea level rise that's happening. I think that there's this really great website here from NASA. It's called the Climate Time Machine. I'll actually go to it real quick and show you an example of what the Climate Time Machine has to offer. I encourage you to check it out yourself. So this is the Climate Time Machine. You can go here. This is a NASA website. So the sea level one that we were looking at, or actually we can look at a different one. Let's look at the carbon dioxide. Why not? And it will take a second to load. And when it loads all of the images, you can kind of drag through time and see the different amount of, in this case, carbon in the atmosphere. I think this is a really nice informative tool about some of the different effects that are happening in climate change. So starting in 2002, we can drag and see how much carbon has been accumulating in our atmosphere. This is parts per million, it looks like. Yeah, so quite a significant change there. And back to the slides, I kind of had another example here where in 3 meters of sea level rise, which is like, I forget exactly what that pairs to, but that's like within the realm of the next few decades to century-ish time. I think the information is more exactly on the Climate Time Machine, but we start to get concerned with losing certain cities, like even in the US, to rising sea levels. So in this case, we lose Miami, which is not very chill, even though there is a chill guy here. We don't want to lose these major cities. This will cost a lot of money and most likely lives as well. So then if we look at the other side of the slide, another indicator or another example of one of the climate change effects is air pollution. And this one I think is a pretty jarring one because so there's a really interesting blurb here that comes from one of the UNICEF reports, and that's that like air pollution accounted for 8.1 million deaths globally in 2021, which is the second leading risk factor for death, I guess, in the world. And found that also like the more than 90% of the air pollution deaths were related directly to the products of burning fossil fuels. So this is, an effect that we would definitely like to avoid, without a doubt. We're losing lives and quality of life from these climate change and fossil fuels effects. And in addition, there's also this like increase in weather events that are happening. So an increase in extreme weather that is also happening. And so the season this past year, so we're currently now in a new hurricane season, although this is referring to the 2024 hurricane season. This was an interesting example. If you're watching this video from maybe in the United States or in Mexico or in North America somewhere, or Central America, and you're looking at the East Coast, or you're in the East Coast of the US or in the East Coast of Central America, or the Southeast of the US, there was a time where we had 3 hurricanes at once. And that was actually has never happened before in our known history of data back to 1851. And, this is just one example of many, many examples. And I'll show some more in a second of extreme and new weather events that we have to deal with as a society thanks to these climate change things. But you might be asking yourself, like, okay, so I talked about the temperature changes, I talked about the carbon dioxide changes, but how do I know that there's a link between the two of them? And how do I know that this is not just like a natural effect? And this, like, I really want to have this like technical conversation because it's something that like I wasn't even really sure about when I started doing this research and getting into fusion and stuff. It's a really valid question to ask. So these things that are called Milankovitch cycles, and these Milankovitch cycles are natural changes in the Earth's climate due to changes in the Earth's orbit. So as the Earth orbits the sun, it precesses and nutates which just means that as it orbits, it changes like how close it is to the sun, and it changes sometimes like where it's spinning and the axis of how much it's tilting towards the sun. There are very slight changes that happen over much longer time spans than a human lifetime. And these do cause natural changes to the Earth, and we've seen them in the past from geological studies, from ice and from rocks that we can do research with. However, there are three main reasons why these cycles cannot explain the warming that we see now in the past like 150 years from the Earth. And let's talk about those. First of all, the Milankovitch cycles operate over extremely long time scales, and these range, I mean long time scales, from like tens to hundreds of thousands of years. Whereas the time scale that we're talking about on the Earth's warming has only really taken place over the scale of decades to centuries. And in the last 150 years, I think this is a really interesting stat. The change of the sun's energy and the change of how close the Earth is to the sun, like how much the sun is putting out, that is, actually have not changed much, but have been shown that over the past 40 years, we've actually had a decreased amount of solar radiation reaching the Earth. So this doesn't really provide a link between any sort of warming, because obviously warming, we would need more solar radiation reaching the Earth. Secondly, Milankovitch cycles are just one factor in a very complex picture. And we actually know that carbon dioxide and carbon in the atmosphere has been known to influence the climate cycles in the Earth's past. And something that I think is really interesting and really ironic is that we talked about isotopes earlier in this course, and the fossil fuels that burn and release carbon into the atmosphere actually leave behind a specific fingerprint because they're a different isotope of carbon than more naturally occurring ones that come from more natural sources. I mean, this is super interesting and ironic because we can actually point out what is in the atmosphere that is not natural, that's from these fossil fuels. And sure enough, we see that this accumulation of carbon dioxide is from these isotopes that come from fossil fuels burning and not natural sources. It's not to say that there are not natural sources of carbon dioxide, but the ones that have really increased in the past 150 years are the artificial ones. And finally, we also know that the Earth is actually in the middle of a interglacial period, which is like a non-ice age type period. And if there weren't any human influences on the climate, we predict that our planet actually should be cooling and not warming right now. And that's following a trend that has been going on for the past like 6,000 years. And that's kind of on par with the Milankovitch timescale length. So these are three reasons why we know things that are happening are not really natural, to say they're more human-based. And now I want to bring you to actually another website here, and I'll just scroll through this website quickly, and I'll encourage you to look at it more yourself. Another NASA website that provides some evidence and some good figures and some good information and sources about why climate change is paired with human development and fossil fuels. So I think, first of all, this plot is extremely, extremely informative. So we can see how much carbon has been in the atmosphere thanks to ice data, like carbon that's been trapped in ice and what is in ice from that's been frozen for many, many years, whether it's like Alaska or Antarctica or something. I'm not exactly sure the specific place it comes from. But we see that there are these trends in carbon dioxide in the atmosphere, and they rise and fall over these 100,000 year timescales. And then we see just in the past 150 years, we shoot up above a line that the Earth has never even gone above before in the past 800,000 years. And this is a pretty clear indicator that something major has changed. It would be a very high coincidence for this change to be just aligning with all of the human things that are happening right now. And in fact, I'm sure there are other geological reasons why we would expect this trend to not have passed this line as well. I am not a geologist. I encourage you to find one and talk to one if you're interested in that. But yeah, so that's one thing. Let's continue to scroll. So generally, scientists do agree on climate change and where it's coming from. Again, I talked about the global temperature rising, the ocean getting warmer, sea surface temperatures getting warmer. There's a lot of good sources here. There's also shrinking ice sheets, glaciers that are retreating. We see less snow cover as well. These are all from like methodical experimental studies and observations. Sea level rise we discussed, Arctic sea ice, and extreme events as well. High temperature events is a big one that's been happening that you may have experienced yourself. Ocean acidification is affecting a lot of the ecosystems. These are all, there's a lot of information here. I encourage you to go read it, read about it, tell your friends, family, this is a very important conversation to have. What is creating these fossil fuels? And what's our progress on renewables right now? So this plot kind of breaks down how many renewables have we, or how much of our energy comes from renewables, how much of it comes from fossil fuels. And we're still pretty heavily in the fossil fuels realm, especially in the US. So this, we still have a lot of work to do in terms of replacing fossil fuels and our energy consumption with mostly renewables. But it's starting, and we're starting to get there. And I also wanted to address another point as well that talks about, so this I think is a very interesting conversation to have because it's been a common conception that fossil fuels will run out within the 21st century. But actually, we've actually been adding to our fossil fuel budget and like how much fossil fuels we have found as we continue to find more fossil fuels reserves. However, of course, we eventually will run out, but it's not really clear when that will happen yet. But this means that the climate change effects like don't stop if just because fossil fuels don't run out. Like obviously, it actually makes it more urgent to get to renewable energies if we're burning more fossil fuels. So this actually makes a really interesting point where we need these clean energy sources that we make, whether that's fusion or something else, to be economically competitive to actually be able to compete with fossil fuel markets as well, and actually be capable of supporting the power grids that will be increasing in consumption as well due to more computing, things like AI, etc. And we also need them to be totally clean. So like this addresses like kind of a nuclear point with fission, with having no long-term radioactive waste, making sure these are really renewable. I will talk about fission in a bit, and I do think fission is a really good option. But fusion is a solution that provides no long-term radioactive waste, can be economically competitive, and is capable of providing enough or more than enough power to power our grid and our society. I think this might be the last thing that I wanted to talk about in this realm, which is energy investment. So I think something that is really awesome that has happened in the last year or so is that there's been a really big jump in clean energy investment. Actually, specifically in China, China is actually blowing all of the other countries out of the water in terms of clean energy investment, as you can see on this plot. And this really shows that the world is thinking about it, and we are moving towards a cleaner energy market. People know that this is necessary. Where the investment is there, and hopefully this trend continues in the next few years. It needs to combat climate change. The next section I have is fusion versus other energy sources. So this is kind of a follow-up from this argument where we can now talk about what is the advantages and disadvantages of using fusion over fossil fuels and over other clean energy sources. As compared to fossil fuels, We'll start off there. So fusion, obviously, or maybe not obviously yet, but there's no greenhouse gas emissions from fusion. And it also has much higher energy density than that of coal, gas, and oil. And we'll talk about why this is important in a bit. But basically, you have more energy that comes out of a sample of the same mass of fuel of coal versus fusion fuel. Compared to wind and solar have some issues because they don't necessarily provide on-demand electricity. So it's hard for the electric grids to deal with that because you kind of need it to be more regular for them to be prepared for what to deal with. And in addition, we can build fusion power sources on the sites of old oil, coal, and gas plants. In fact, this is actually what's happening for the first site that's planned in Virginia. It's at an old, I think it's a coal site, and basically you just take out the coal burning part and you put in the fusion part and you connect everything to the power grid that way. Wind and solar can't necessarily do that because they need like wider areas and whatnot, but this is something cool for fusion. And for fission, we have the abundant fuels that are used for fusion, deuterium namely, are not radioactive and they are extremely abundant. Tritium has some issues as the other fusion fuel. It is slightly radioactive, and I will talk a lot about that on the next few slides. However, it is nowhere near as hard to deal with as uranium is for fission. And the products of fusion are also not radioactive. There are some connotations with that, but not nearly to the extent, again, it's not nearly as hard to deal with as with fission. There's also no risk of a meltdown in a fusion power plant. Even though fission power plants are very safe now, there's like physically no risk of a meltdown in a fusion power plant. And there's no direct weapons applications. You're not making like uranium or like weapons grade uranium or anything like that. And there's no concern for like a surrounding community if a fusion power plant was in like a surrounding community. This is because fusion can't melt down. It doesn't like release any harmful gases or anything into the river supply or anything like that, or into the water supply. So it really is safe to have like in a community or near a community. I wanted to talk a bit about this no risk of meltdown thing because in fusion power plants, can't melt down because you need heat to get fusion to happen. We talked about how hot we need to get. We need to get to like 100 million degrees Celsius. So when something goes wrong in a fusion power plant, what happens is the plasma that's containing all the fusion the first thing that will happen is it will be not confined and it will shoot itself into the wall of the device. Now, the wall is much colder than 100 million degrees, and it immediately cools down the plasma. And you pretty much immediately lose, although your wall might heat up, you lose the ability to do fusion. And that's why you can't melt down. There's no like runaway effect that can happen because when something goes wrong, you lose the ability to do fusion. Whereas in fission, if something goes wrong, you actually make the ability to do more fission. And that's why there have been meltdowns in the past at a very basic reason. Now, all this is to say, I really do like fission. I think fission is a really great option and a great stepping stone to fusion. I think fusion is the long-term solution, but I'm also a big advocate for fission. It is extremely safe now, and it is very high energy dense. And there are power plants that exist in countries that, run mostly off of fission. It's safe, effective, clean. So I'm a big fission supporter as well. I don't want to make that wrong impression. And now we can talk about the fusion fuels, deuterium and tritium. So deuterium and tritium, these are the most common choices for fusion fuels. And we'll talk about why in a second. And reminder, deuterium is 1 proton, 1 neutron. Tritium is 1 proton, 2 neutrons. And they're all happy on this slide. We're all happy. But deuterium is really great. Tritium is a little bit hard to deal with. And let's talk about why. So first, just a reminder, remember when we have deuterium and tritium, we have this neutron that comes out and we have helium as well. And this is the splits of the kinetic energy that comes out of these interactions, this process. Also something to note, the kinetic energy of the reactants, the tritium and deuterium, is actually very small. They really are not even close to as kinetically energetic as the products of this process. Why is deuterium and tritium, or DT, the main focus? As I've been saying, it's the most common choice for fusion fuels. And that's because it's the easiest fuel source to achieve net energy, and that's because of this graph on the screen right now. So what is this graph showing? So on the y-axis, on the vertical axis, we have total reactivity, or something that is often referred to as a cross-section. And these metrics are directly related. I think it's just easiest to think of it as how likely is it that a fusion process will occur given two types of particles, so deuterium and tritium, or deuterium and helium, helium-3, a proton and boron-11, deuterium and deuterium. One of these lines exists for all types of particle interactions. You could theoretically try to fuse any two particles together. Just some of them are going to be much, much harder than others. In this plot, and on the horizontal axis is ion temperature, or the temperature of the two reactants, so maybe deuterium and tritium. And I think it's worth it to note that what's called a keV, which is a kilo electron volt on this plot, is about 11,000, I believe. Sorry, that's not 11,000. That's 11 million, 11 times 10 to the sixth. You can check the phrase that I'm using there, but it's a lot of temperature that's needed for these interactions. Why do we need deuterium and tritium? Is because, so let's take a look at the peak of this deuterium and tritium. Say that's where we want to be. Say it's at maybe that's 20 or 30-ish keV. If we want the same amount of reactivity, or the same amount of fusion to happen but use a different fuel, we actually, on this plot, we can't even achieve the same amount. So let's actually take it down. Let's go down to where the peak of the deuterium and helium-3 curve is on the deuterium and tritium curve. So that's around maybe 8 to 10-ish keV that it crosses the deuterium-tritium curve. If we wanted to create the same fusion reactivity, or the same fusion amount of fusion that's occurring, we'd have to go to the next highest reactivity, or the next highest cross section. Is this deuterium helium-3? We'd have to go up to over 100 keV. This is a 2 order of magnitude increase, and you would be going from 11 million, or you'd be going from 10 million Kelvin to over 1 billion Kelvin, which is just an enormous jump. Then it's something that's not really obtainable. And this is actually around on the deuterium and tritium side of things. That temperature is around where fusion power plants might be operating, maybe a little bit hotter, but it's just way too hot for any other type of atomic combination for at least our technology right now. And that's why deuterium and tritium is kind of almost necessary for doing fusion at the technology level we have right now. Otherwise, it's just too hot, or just not enough fusion is happening, at least in these first generation devices that will come out. Maybe there are some people that argue against me, and I would love to see a fusion device that doesn't use deuterium tritium, but it seems like the trajectory is going to be deuterium tritium for now. So there are, in the other types of atomic arrangement, or the other types of atomic combinations, you actually get different atomic products as well. So not the neutron and the alpha particle, but maybe there are different versions of things that come out. And this actually might change the exact mechanism in which you are heating your water and spinning a turbine, or doing something maybe slightly different to actually get electric energy out of your fusion process. I won't talk about those here, but those are kind of interesting pathways to pursue in fusion research. And now DT or deuterium tritium, it's not perfect, although it has this very high cross section. And that's really because of tritium, as I've been alluding to. So now let's talk about tritium. One of the first issues before we talk directly about tritium is these high energy neutrons that come out. And this is one of the concerns with fusion power plants, is that when you have materials that are subject to high energy neutrons, and these are like extremely high energy neutrons, even more energetic than neutrons that come out of fission processes. We don't really know what's going to happen to the surrounding materials. And this is like all contained within the actual fusion plant itself. This is not like threatening surrounding communities and stuff, but like in terms of the structural materials of the plant, they may be pretty problematic for those materials. And this is something that people are starting to do research on now as we prepare for power plants that might operate over the span of decades or years or so. Tritium is also not plentiful. It's actually extremely rare in nature. We would have to make most of it. And this is actually a big problem. There's not that much tritium currently in the world. And I think on the next slide, I'll talk a bit more about that. But tritium is also radioactive. So handling it is non-trivial. You have to be pretty careful when you handle it. However, I mentioned that it's not as hard to handle as uranium, and this is because of its half-life. So when you compare it to fission and you're using uranium. So in tritium, or most fission things use uranium-235, I believe. I'm not a fission expert, but tritium has a half-life of about 12 years. So that means that if you have a kilogram of tritium and you put it somewhere and you wait for 12.3, 2 years, you come back, half of it will be gone and will have decayed into something else. For comparison, uranium-235 has a half-life of about 700 million years. This is why it's really difficult to deal with fission waste other than just like burying it and leaving it there. Whereas fusion waste is a little bit different. And actually, I have a funny anecdote about this. And that's that, so as part of my personal fusion journey, I worked as a SULI intern, which if any of you guys are in undergrad, I encourage you to apply to the SULI Department of Energy program. That's SULI. It's a fantastic program. I had a great time and it propelled me into this field. So Princeton has Princeton Plasma Physics Laboratory where they have fusion devices there. And these are some pictures of me at the fusion device. This device is called NSTX or NSTXU. It's currently being rebuilt or upgraded. So you can kind of see inside of the fusion experiment there in the middle picture and top down on the picture on the left. So the anecdote that I wanted to tell was that so my mentor he worked on this project, or he still works on this project at Princeton, and he was giving me this tour. And when we were going into the facility that this device is in, I saw there's this box that's kind of like in the middle of a field outside of the device. And I asked him, I said, hey, like, what's that box out there? And he was like, oh, that's where they put the tritium when they were running tritium in this device. And when they were running tritium in the device, I think it was in the 70s or 80s. And I asked him, I was like, isn't that kind of dangerous to just like kind of keep it in the middle of the field? And he said, well, maybe, but the tritium that's in there actually is almost completely gone because it only has a half-life of 12 years. So if this was done in, say, 1980, that was what, 20, 30, 45 years ago now. So you've passed almost 4 half-lives. So you're down like well below 10% of the amount of tritium that was in there originally. And this is a reason why it's easier to deal with tritium than it is with something like uranium, because if you have leftover, you need to discard it. You can just kind of put it in a safe place for a little while, and then you'll no longer have to worry about it. I think something else that I also wanted to mention before I go on about tritium is that these neutrons as well that come out of, on the topic of radioactivity, might make the surrounding materials radioactive as well. And they might activate some of these materials like on the surrounding walls of the fusion device. Again, not a threat to any like community, but just within the device itself. And this might this might make some radioactive waste that needs to be dealt with as well. Although, again, it's pretty minimal and would be contained just like within the device itself. All things to learn about with future research and fusion devices and power plants. So I mentioned that tritium does not have a lot, like we don't have a lot of tritium. However, we do have a lot of deuterium. We have enough deuterium in the ocean to supply 60 billion years of, I guess, fusion interaction. I'm actually not sure exactly what that metric refers to, but there is a lot of deuterium in the ocean. We would not have an issue of getting deuterium or lithium. And the reason I bring up lithium is because a interaction between lithium and a neutron, a high energy neutron, actually creates tritium. You can make a nuclear process that will create tritium and helium from this interaction. So you might see where I'm going with this. If you surround your fusion device in lithium with lithium and you propel the neutrons that you're spitting out to lithium and instead heat up a lithium what's called a blanket as opposed to, or just like a pool of lithium as opposed to a pool of water, you could generate heat and electricity, and you could generate tritium from that process. So you could actually get more tritium. This is what we call breeding tritium out of fusion power plants. And this could solve our tritium, like our lack of tritium issue that we're dealing with right now. So an example of like how this would look would be, and this is the ARC reactor, which is what a company called Commonwealth Fusion Systems is planning to build for a fusion pilot plant. There's a lot of information on this slide, but the thing that I want to direct you to is the what's called the FLIBE liquid immersion blanket, which would sit inside of the magnets in the fusion device. And we'll talk a lot about like the structure of everything that's going on here. All you really need to know is that the plasma is shown kind of in this like greenish, tannish color in the center there. And surrounding it immediately is this FLIBE, which has lithium in it, blanket, and that's how we could produce tritium out of a fusion device. There are some other ideas for solutions to making tritium. One of them is using fission plants. So there is things called CANDU reactors, and they can actually generate tritium, and they actually might help for before maybe we get fusion power plants online first without tritium blankets to surround our device, and these might produce fusion power, but we need to supply the tritium from somewhere else. We could also create like external tritium sources. Tritium kind of has to be controlled under regulations a bit, although regulations in fusion is a very big field that is also really great to go into and really defining the regulations of what we need to do as we're developing a power plant politically. But with tritium, there are some weapons applications as well, which makes it harder to regulate, or which makes it like just more regulated, and again harder to deal with. But this also kind of departs us from the fusion mission if we're not developing tritium on site of a fusion power plant, because the whole idea of fusion is to make it a self-sustaining, a very sustainable and self-sustaining process. So we don't want to rely on things that are less sustainable, like a fission power plant, even though, again, fission is like a good stepping stone. Like it's not totally clean, but it's much cleaner than fossil fuels. So at first, we might have to rely on them, but it's not exactly clear what the best path will be for this. There's a lot of research going on about how to best create the tritium market that we need to do fusion and to have a fusion run society. In fact, an interesting stat is that there's only a few tens of kilograms of tritium that are currently in the world. So we definitely need like tritium production for long-term use and just to get our power plant started. And this is a bit misleading because a few tens of kilograms of tritium is, you don't need that much tritium to do a lot of fusion. like even just a few grams is like all makes a lot of fusion power, and we'll talk about those metrics in a second. But on a power plant scale, you definitely need more than this. So in fact, how much deuterium and tritium would we actually need? So this is, I think, the biggest advantage of fusion power over other energy sources, and that's that fusion is just incredibly energy dense. So a great example of this, a great analogy, is that to produce 1,000 megawatts of electricity for one day, which is enough for like a major city, you need 18 million pounds of coal. That's like 80 railroad cars filled with that. So imagine like a train going past you for just like you're stuck at that train station for a while, and it's just all coal that's going past you just for one day. Whereas a DT power plant, a DT fusion power plant, only needs 3 water bottles filled of deuterium and tritium to create enough power for that one day. That's just like a major difference in why fusion has the chance to be so economical and is just so efficient as well. And we can have so much power. And in fact, like this quote, the fuel for fusion, this is talking about deuterium, can be extracted from seawater and a bathtub and 2 laptop batteries. I believe that's referring to the lithium to create tritium from a deuterium tritium interaction is actually contains enough energy to or enough fuel to create enough energy for an entire lifetime of somebody. And that's just like really an incredible statistic that fusion has the ability to do. Whereas, coal, we need so much of it. So this is a big advantage of fusion. And now the actual numbers of the energy density comparison. So fusion is actually about 4 or so times more energy dense than fission. And energy density, I didn't define it explicitly, but here you can kind of see. So this is in units of energy per mass, or this is gigajoules per gram or kilojoules per gram on the screen here. These units are not super important. It's more of a comparison. You just need to know that energy density is how much energy you get out of some set amount of mass of a fuel. So DT is about 4 times more than fission, and DT is about 1,000,000 times more because that's kilojoules, not gigajoules. So a different prefix. It's about 1,000,000 times larger than methane. And again, that's like the big reason why it's so advantageous over things like fossil fuels in terms of just energy production. And just to drive this point home, some more stats, I think actually, and this is kind of an interesting thing of this is again energy density, another measurement of energy density compared across different types of production methods. And another fun stat, a pickup truck filled with fusion fuel has the equivalent energy of 2 million metric tons of coal for 10 million barrels of oil. That's just like so, it's so crazy, that comparison. Something I think is interesting is the only interaction in, I believe, the universe that is more energy dense than a DT fusion interaction is an antimatter-matter interaction. I believe this is antimatter-matter annihilation. I don't think this is antimatter fusion, but an antimatter-matter annihilation event is more energy dense. However, we don't really have access to much antimatter. It's very hard to create and collect antimatter from our surroundings, probably even harder than it is to get tritium. So the basis for doing antimatter-matter interactions as energy source is not really within the cards yet for us as a society. I think fusion is a bit more developed than that. There's also a poetic reason why we should use fusion to power our society. I think this is a very nice poetic reason to use fusion, and that's that fusion is kind of already responsible for all life on Earth, and in a way, all other energy sources. And that's because fusion is the energy of the universe. All the stars in our universe use fusion to produce energy. They do it through gravitational just compression of using gravity to just compress particles like so much so that they fuse together, and then they release all this energy. And this is, this is how the sun is this giant ball of plasma. It's super hot. It's hot because of the fusion that's happening in it. And we're here because of the sun. And we've developed all of our energy sources thanks to the sun. So, in a very real way, fusion is the energy of the universe. It's kind of poetic to use it for our society as well. But there are also a lot of practical reasons that we've just discussed. Our next section is the history of fusion. So now we know a bit more about what fusion is. We've talked about the advantages and some disadvantages even of it. Now we talk about what's our history, where are we coming from? So again, to do fusion, we have to get over this Coulomb barrier, or this electromagnetic force barrier. And we need to find different ways to tackle this problem, to get over this barrier and get to the strong force. We'll start at the beginning of time, because the first stars in the universe, as I mentioned, stars do fusion. So stars have figured out how to do fusion by having enough gravity to push its particles together enough so they overcome that Coulomb barrier, the electromagnetic force, and the strong force takes over and they fuse. Stars have so much gravity that they're able to do this. Obviously, we can't really do this on Earth. We don't have enough mass to do this. But with the mass of stars, they can produce and create self-sustaining fusion interactions that just continually support fusion for billions of years. Stars can live for billions of years and do fusion for that long. So how do we do this on Earth? We look at the sun and we say, the sun's doing fusion, so maybe we can. The sun is big and powerful, but we don't have enough gravity to do so. And we think about it really, really hard. And we've come up with a few different ways to do this. So there's some alternatives to gravity that humans have thought of and created for creating this like immense pressure and forces that are needed to overcome the Coulomb barrier and make fusion. Plasma accelerators are one of them. Magnetic fields are another way that we can create pressure and lots of pressure. Lasers are another way. Pistons in like a mechanical way is another way. There's a company called General Fusion that has been working on this. This one's very interesting. I won't talk about it more than I am right now, but it's interesting to check out if you're interested. And also doing creating pressure from electric currents as well. And this is done from companies called some companies are doing it. There's one called Zap Energy that's really into this in a device configuration called a Z-pinch. Again, we won't talk more about that currently, but that's also an interesting path. So we'll talk about two versions here. We'll talk about lasers a little bit, and we'll talk about magnetic fields for how to do fusion. So first with lasers. And I wanted to talk about this because there is a very large effort into doing laser fusion in the fusion community, and it's actually been very successful so far. This is called, fusion with lasers is called inertial confinement fusion, or ICF. And sorry, there's the triple product is mentioned on this slide, but we have not discussed that yet. So you don't have to worry about that just yet. We'll talk about triple product a bit. But to do ICF, you have to, and again, we're doing deuterium tritium here. You have to compress DT like super, super fast and confine it for a very, very short amount of time. And by doing so, you can get these like very large energy outputs compared to the energy that you put in. This ICF is mostly a military application. However, there are some clean energy versions of it, but you need like a lot of cycling to get large energy output, because usually these interactions, the high energy dense or the high energy yield and like net energy in versions of this happen on very small mass scales. Like the mass of a DT pellet is only outputting like a few megajoules of energy, whereas like a city would need much, much, much more than that. So you need some sort of cycling, which isn't really like a technology that exists yet. But that being said, you may have seen in the news at some point that in the past few years, we actually, there are scientists at NIF, or Lawrence Livermore National Laboratories, that National Ignition Facility, that actually broke net energy or got more energy out of a fusion process than they put into it. And they achieved this, and this was a huge scientific achievement. It's never been done before by humans. So, but let's talk a little bit about like what that actually means. So, in order to do NIF's ICF and do their inertial confinement fusion and shoot these lasers at this deuterium and tritium pellet, you needed a facility that was this large, like how large you can see this on the screen. This facility, let me get rid of that. This facility is actually the size of, I believe, have a comparison to 3 football fields just to shoot in a 10-meter diameter chamber or at a pellet that's you could hold with your 2 fingers of deuterium and tritium. So it's a lot to get that energy out. That's where the target chamber is. And I want to talk about, so you might say like, okay, that's a lot of stuff to put into this pellet. How do they get more energy out of that than they put in? And it's all about where you draw what I call a control volume, or where you say, I am putting this much energy in and this much energy out. So the achievement that was that NIF had, and I'm by no means belittling this, but it's important to know what the comparison is. So when you put energy into this deuterium and tritium pellet, you're shooting it. You first have to take a bunch of power from the grid and put it into all your lasers, and then shoot your lasers into your device. And where they draw their control volume is around the pellet itself. So they say that, okay, around the pellet, I'm putting 2.05 megajoules of energy via lasers into that pellet. That's the amount of energy that's going across this control surface that's surrounding this control volume. And then coming out of that from fusion is 3.15 megajoules of energy. Actually, now it's even greater than that. It was their high, I think, I haven't checked recently, but within the last few months, their highest one was like 5.2 megajoules. So, they get about more than 2 times the amount of energy they put in out. However, it's not the full amount of energy that was required to power the thing. It's only the amount of energy that was crossing that control volume. You could draw your control volume all the way back to where it's drawing power from the grid, and that's like 300 megajoules of energy. So it's important to make this distinction here. And we'll talk about, this is really defining like how we define scientific energy gain versus engineering energy gain versus economic energy gain, and how that's important when you're developing a power plant, because it might be sufficient if we can get this to be economically viable to have maybe not an engineering energy gain where we're not, maybe our full control volume isn't net energy, but also like this kind of could go on forever and ever, because you might say, well, okay, so how did so we have this grid, or we have these lasers. Where did we get the energy from the lasers, from the grid? Okay, but where did we get the energy to build the grid from, right? So you could kind of continue to trace this back, and at some point you need to draw a volume, a control volume, and really that control volume that matters is usually set by economics and like how much money can be produced from these devices. That translates to energy, and is it going to be viable for our society to support it that way, and for people to invest in it, and for us to sustain it economically as well as engineering wise, because we can do it engineering wise. It's just, is it efficient? So again, scientific versus engineering versus economic breakthroughs depends on where you draw your lines. I think it's a very important conversation to have when you're talking about scientific breakthroughs. Okay, so that's lasers. Now let's talk about magnetic fields. So magnetic fields, or magnetic confinement fusion, or MCF, is the main energy method, or the main idea for energy production, and it's like the energy sector's choice of fusion. And that's what we work on mostly at the Columbia Plasma Physics Lab. It's what I work on mostly. It's what we'll talk about most of the time for most of the for most of the classes in this class. So basically what we do is we have a large volume and we put magnetic fields. So we'll talk much more about this in later courses or in later classes in this series, but charged particles follow magnetic field lines to lowest order. So if you have a magnetic field line, there's a charged particle in a plasma that's moving along it. You want it to stay in the same place. So what would I do to make my particle that's extremely hot stay in the same place if it follows a magnetic field line? Well, I could make a magnetic field, and then I could wrap the magnetic field on itself, maybe in a donut shaped, like is shown on the screen. And that's indeed the basic idea behind most magnetic confinement fusion devices. It's just make these magnetic donuts that cause particles to just stick to the field lines and just go in a circle around and around this donut. Now, these field lines actually have to twist for other effects because these particles don't only stick to the field lines, they actually drift off of them a little bit. And we correct for this by actually twisting the magnetic field lines. And I'll explain much more about why these field lines are twisted. Or actually, I probably won't. It will probably be in a future lecture or in a future class. There is a nice analogy for this. It's like a honey on like one of these honeycomb sticks. Keeping these particles confined is kind of like twisting the honeycomb stick as the honey is falling off of it. So it's being pulled off of the honeycomb by gravity, like these particles are being pulled off the magnetic field lines. But as we twist the field lines, like as you twist the honeycomb stick, I guess the viscous forces or the friction from the twisting is actually keeping the honey from falling down and succumbing to gravity, similar to how the twisting of the field lines is keeping the particles from succumbing to the forces that are pulling them off the field lines, which is a variety of things. And in magnetic confinement fusion, there are two major types of devices. There are a few other alternatives, but the two largest funded ones and most probable ones to contribute to at least the first generation of fusion power plants, or the first few, are tokamaks and stellarators. So a tokamak is one of these giant donut devices, and they have magnets that create what's called a toroidal magnetic field, which goes around the donut long ways, and a poloidal magnetic field, coils that make poloidal magnetic fields, and that's what goes around the donut the short ways. And you can kind of see that on the screen here or on the previous slide. These tokamaks are what's called axisymmetric. So if you slice the donut or the tokamak at any point, kind of up and down, and create a plane that's shown like a section that's shown on the screen here, you'll get the exact same cross section, or the section that you see of the slice you've taken of the donut, the tokamak. You'll get the exact same one of those at every point that you slice. That's called axisymmetry, and that's what the tokamak really is. The stellarator, on the other hand, is the same thing as the tokamak, except you take away this axisymmetry. So this is one of the stellarators that exist in the world in Germany called Wendelstein 7X. Instead of slicing it at every point and seeing the same section, it's still a donut, but you slice it at every point and you see different sections. And this gives us more ability to contain particles in different ways. It gives us a little bit more freedom to move the fields around, the magnetic fields around within the device. But these devices then become a lot more complicated and like twisty and whatnot. Some stats, so in a tokamak, you actually have current that twists your magnetic field and helps your particles stay on the magnetic or within the device. The longest pulse that has been created in a tokamak was in a device called West, and that was about 6 minutes. The largest Q, and sorry, again, we haven't talked about Q yet, but this is like energy gain, has been 0.67. So one would be net more energy out than in. We'll talk more about Q factor in just a bit. And that was by TFTR from the Princeton Plasma Physics Lab. In the stellarator, the longest pulse duration was around 8 minutes from W7X. The equivalent Q from a tokamak was about an order of magnitude below that. It was actually JET that produced this Q, not TFTR. Okay, so talking a bit about the history of fusion now. As we have gone over a few of these events, Now we can look at it on a larger timeline. So, way back about 13.8 billion years ago, we had the Big Bang. First stars start forming a little bit after that. And we jump ahead. So as first fusion happens, jump ahead a few billion years. The first development of plasma physics theories and fusion theories happened in around the late 19th century or early to mid 20th century. Then the first stellarator device, the first fusion attempt at a stellarator, was created in 1951. The first tokamak was created a few years after that. And then the US and most of the world decided to focus on tokamaks a few years later because tokamaks were seeing a lot better performance than stellarators were at that time. And then we had a funding wall that existed between the late 80s and early 2000s. But in that time, JET produced the Q is 0.61 shot, which again, apologies, we haven't talked about Q yet. We will in a second. But produced the highest fusion output shot that we've done so far. And then the stellarator came back with the building of W7X. And then there was kind of coasting for a few years. And in the past 10 years or so, there's been a big jump in funding again, where private industry has also joined, especially in the US and in some other European countries as well, with the introduction of the computer and more powerful computing, we have better designs, stronger electronics, we can just create stronger devices in general. So there's a really big push for fusion that has been happening very recently within the last few years. NIF's net energy achievement, Q is greater than 1, which again, we'll talk about in a second, happened only a few years ago, and then here we are today. And this is just kind of like an image of what's going on with the federal budget and fusion, I believe. So we had, there was a big budget boost in the 70s, and then things kind of tanked in the 80s and leveled out for a little while for fusion. And then very recently, the budget has started to skyrocket again. And in fact, the private industry budget is now surpassing the public sector budget in the US. So there's really a lot of emphasis in private industry now on fusion, and economically it's being reflected as well. So there's lots of new devices being created, and we'll talk about a bunch of them in just a few minutes. Okay, so that concludes the history of fusion section. We'll now move to fusion as an energy source. So let's talk about how we actually make fusion devices and how we use the energy sources. So now we can finally talk about the triple product and Q as well. And we'll talk about how we make fusion devices, and then we'll talk about where we are in making progress towards power plants. Let's first talk about the triple product and Q. Okay, so these are performance metrics for fusion. They're two metrics that we use to measure how well is a fusion device performing. So there are three major things that go into the triple product, and then we'll talk about how it's related to Q and what Q is. So the triple product is a performance metric that has three criteria: temperature, density or pressure, and time. The pressure one is really density or N. Temperature is capital T, and time is lowercase t or tau, usually. So the reason we multiply these three metrics together to create the triple product, because it indicates, like, each one of them indicate a direct metric of how fusion is happening within the device, or how much fusion can happen. So higher temperatures mean that more fusion will happen. The energy of particles will go up, and thus particle collisions will be more likely to do fusion. The pressure or density, or the space between particles, means that particles are more likely to collide if you have more density. And how much time the particles have to explore their environment as they randomly move around is also how much time they have to potentially collide with each other. So all three of these, increasing them will make more fusion, and that's why we multiply them together to create the triple product. So the greater the product, the more fusion performance there will be, or the better fusion performance there will be. And there have been analysis then, namely one by John V. Lawson in the 50s, where you can estimate what you need from the triple product to create more energy out than is lost from your fusion processes. And this is called the loss criterion. So if you have net energy or more energy produced than lost, or more energy out than in, you need a triple product that's greater than this loss criterion. And this is directly related to Q. So Q is dividing the energy out by the energy in. So this is why Q greater than 1 implies this net energy, more energy out than in. So in order to do a power plant conditions are estimated to, and remember, power plants need to be economic as well as producing a lot of energy. That's actually how they're economic. So you need to have a Q greater than 10, or that's what it's estimated at least. The connection to the Lawson criterion is that if you are calculating the Lawson criterion for your specific device, and you take into account all the forms of energy loss that you're getting, when the Lawson criterion is exactly met, you have Q equals 1. And you can apply these metrics to any type of fusion device, whether it's magnetic, whether that's inertial. I guess these are more in the magnetic confinement ones. So any type of really magnetic confinement fusion device, for the specifics of it, I think you can extend to a few different other types of fusion devices, but especially any type of magnetic fusion device, you can have a Lawson criterion and a Q value for. So it's good to look out for these when you hear different developments have happened in the fusion community. You say, okay, a new plasma has been created that's been very powerful. Maybe you asked, okay, what was the Q value that came out of that plasma? That should be pretty telling. But now, where are we drawing our control volume for energy in and out? We were talking about that before. I've been talking about energy out and energy in, but I haven't told you where the control volume is. So when I say our system is losing energy, what does that even mean? And now we have to define these different Qs. So Q scientific, engineering, and economic. This is directly related to what I was saying before about where we put the control volume. Do you put it outside the device? Do you put it outside the fuel? Do you put it, like, how did you make your grid? Or how did you make your input power? These are all questions we need to ask. So for Q scientific, we say that the input is the power provided by the plasma or the power provided to actually heat and start up the plasma. And the power outputted is the power that leaves the device before heating the water. So you can kind of imagine a control volume that's exactly around our plasma almost. That's the scientific thing. For engineering, we say, okay, the Q engineering is the input power drawn from the grid, and the output power is the power provided to the grid. And this roughly equates to about 10 times the scientific. And now the economic one is a little bit different defined. It's the cost of power from the grid, that's the input, and then the revenue from the power provided to the grid, that's the output. Now, what actually matters and what do we usually refer to? Well, first of all, it's not totally clear in it's supposed to be, sorry, that's supposed to say economic, but it's not totally clear how a scientific Q and an engineering Q relate to the economic Q. That has lots of complex analysis that's needed for that, and changes with time and how different materials change prices and processes change prices and inflation and whatnot. But we really need this economic Q to be advantageous because, or high, if we want to, well, first of all, we need it above 1, so we actually are making money if we want our devices to be economic and for people to invest in them. For scientific and engineering, and that's, again, these are to have Q economic greater than 1. These are simply for economic reasons. There are many non-economic reasons that we should invest in fusion that I've discussed with climate, and with there's also energy independence and just sustainability in general, and competition with other countries as well, to be supporting our computing resources, and then, yeah, as a society in general, just having more access to electricity. However, the the purely economic incentive, needs this Q economic above 1. However, that's not quite what we say for our research achievements. For our research achievements, we normally use Q scientific. So Q and Q scientific are usually one and the same. So that means that the NIF achievement, where NIF went above Q equals 1, more energy out than in, was a Q scientific achievement. And again, Q scientific is input power provided to the plasma, so kind of drawing your control volume directly around your fuel, and then output power coming out of your fuel or out of your plasma. And sure enough, NIF actually does use plasma as well, even though it starts as a solid pellet for their fuel. Finally, defining ignition. Ignition is a region of when you're operating your device where the plasma is self-sustaining. So it's not necessarily paired to a specific Q value, but it's when you have enough heat coming out of your fusion processes so that the plasma is maintaining itself being hot, assuming you have good confinement, and you don't need your external heating. And that occurs somewhere above Q equals 1. And actually, NIF has achieved this when I don't know exactly when the threshold for ignition was crossed, but they've achieved about, last that I saw was Q of 2.2 at ignition. And a burning plasma is something that is a plasma that has achieved ignition. That's just a good term to know. Okay, so how do we actually make a magnetic confinement fusion device? Let's go through the basic steps. So first, we take, we'll go through this layer by layer. So we'll first take a vacuum chamber. And now this vacuum chamber, we need it to be in vacuum so that we have as pure fuels as we can, so that our plasmas are as simple and we are controlled as possible, and our fusion interactions, what things are colliding with, what particles are colliding with what, are only deuterium and tritium. So we make a vacuum chamber, we take all of the air out, and then we take everything out of it, the air and all other gases, and then we put in the fusion fuels we want, so probably deuterium and tritium as gases. And then we initiate the breakdown of this gas into a plasma. So that means we have to start heating it. And I'll talk a bit about how we do that heating in the next few slides. And then we heat the plasma more using radio waves or electric fields, or sometimes we shoot neutral particles into them, and then magnetic fields, and we use these magnetic fields also to confine the plasma. So we just continue to heat it until we can get to fusion temperatures. And then we make sure that plasma is confined using magnetic fields. And this is how these are what separates, this step 4 is really what separates devices within the magnetic configuration, within the magnetic confinement fusion configurations. We have tokamaks, we have stellarators, which we've talked about. There are other types of devices. Some of them are called field reverse configurations, and there's even more types of devices than that. Okay, so how do we actually create this breakdown? How do we actually do this plasma startup? How do we take a gas, make a plasma, and then start actually heating this plasma? So one example of how to do this is with something that's called ohmic heating via the part of the device that's called a central solenoid. And the central solenoid or the CS, is this stack of coils that runs through the center of the device. So you can kind of see on the device, you see the two toroidal field magnets that look like a D flipped on itself. So there's one D, and then it kind of, this is a cross section of the device, and it mirrors around the central solenoid. The central solenoid is shown in this yellow, tannish orange color in the middle. And when the central solenoid starts up, it starts changing its magnetic field. So it's a giant electromagnet, and it starts turning on its magnetic field. And it basically makes an electric field that runs around the device as it turns on. So kind of looking at a top-down view, the electric field starts to circle around the central solenoid. And as it does that, any free electrons that are within this sample of gas are accelerated by this electric field. And in fact, thanks to cosmic rays that come down from outer space, any free sample of air will have any free sample of gases that are on the surface of Earth will actually be ionized by these cosmic rays, and they will create these free electrons that are just kind of floating around normally in a sample of gas. This is actually really cool. This is why we're able to create plasmas in this way by just applying an electric field, because these free electrons will be accelerated and hit into the surrounding atoms and start to knock electrons off of those, and then the effect cascades, and you start to get a plasma that has a lot of free-floating electrons and free-floating positively charged ions then, or the nuclei that were ionized. So this is, yeah, I think this is a pretty cool fact that thanks to the outer space cosmic rays, the high energy rays that are coming down, we can actually create plasmas in this way, and we have free electrons in these gases. Also, fun fact, and apologies, we can't do any demos with this because I am a person on the screen in YouTube, not necessarily in person with you guys, but we can, because these electrons, so we learned in the last few classes that electrons that accelerate will emit light, emit radiation as well, or emit electromagnetic radiation in the form of light. In order to emit visible light, electrons have to accelerate at a very specific rate. They have to they have to be emitting in the visible light spectrum. We looked at the electromagnetic spectrum before. Fusion plasmas are actually so hot that the electrons are emitting electromagnetic radiation that's much, much higher energy than visible light. So fusion plasmas actually don't normally glow. They're invisible to us because the energy that they're emitting is such high frequencies. So, they're like way past the visible light span or the visible light range in terms of what electromagnetic radiation the electrons are emitting. So again, we talked about the recombination and acceleration processes in previous courses that create light. When these electrons are accelerating, we are now hanging out in the range, maybe in the ultraviolet or X-rays, or yeah, I'm not sure the exact highest point that we've reached of radiation that comes off of these fusion power plants, but they do tend to be above visible light. And we can actually see that with cameras, or we can see the lack thereof with cameras in this example. So I believe this is JET, a tokamak that has now been decommissioned, but this is an operation of JET. And you can see that, well, actually, you can't see in the middle of the device is actually where the plasma is most prevalent and is densest and hottest. However, you can't see that part. You can only see the edges of it. And that's because the edges are much cooler and actually are emitting visible light, whereas the middle is much hotter and not even emitting visible light. So I think that's a very cool visualization. This is a real camera. Okay, and now how do we actually extract this energy that's coming out of the device? So we've built our device, and before we talked about we have a neutron and an alpha particle that come out of this fusion process with deuterium and tritium. Neutrons will heat the blanket that we've surrounded our device with, whether that's filled with water or filled with lithium. And neutrons are extremely, extremely hot, almost 12 billion degrees Celsius, and they collide with everything around. They're not charged, so they fly through your device walls and through the magnetic fields. They don't get affected much by that. The spin effects are not super important. And when the neutrons get ejected from the fusion processes and they fly through your device, they can directly heat a blanket of water or heat a blanket of lithium and breed tritium at the same time. And you can then heat water via heat exchanger or I don't think you'd spin a turbine with lithium. You'd probably have to use water as well, but I'm not super sure about that. And then you'd have to extract the tritium from your device, which is a whole other issue. So this is how you use neutrons to get energy out of a deuterium and tritium fusion power plant or fusion device. Obviously, 12 billion degree Celsius neutrons are quite energetic, and they are very hard to deal with coming out of your device in terms of like materials and stuff. And we talked briefly about that before. Having materials that can sustain that type of bombardment. Now, the alpha particles, they first collide with ions within your device, and they're contained within the device, or they need to be, to continue the heat the plasma and continue the conditions required for fusion. And once they deposit their heat, they can be forced out of the plasma, or they should be forced out of the plasma by some instabilities to the device top and bottoms, and they exit the device via these things called diverter plates. And now the diverter plates are things that must be extremely strong and have very high melting points and be hopefully they might be able to be actively cooled as well. But with these diverter plates, they have to take an extreme amount of heat coming out of the device. And they take the bulk of the heat that comes out of the device. So for example, the diverter plates might take about 1 × 10⁷ watts per meter squared of heat flux coming out. The sun provides about 1 × 10⁻³ watts per meter squared at the Earth of energy. So this is 4 times greater than the sun's intensity of heat that's coming out, or that intensity of heat that's coming out of a fusion device. So it's a lot, and making diverter plates that don't melt is a big task in the fusion field. It's a lot. Yeah. So kind of looking from taking a step back and looking at what a fusion power plant might look like. So we've talked a lot about the actual fusion part itself. And then we talked about how there's tritium breeding blanket fluid that comes out and is met with a heat exchanger to exchange to water to heat up water. That water creates steam. That steam runs through a turbine, spins the turbine, spins that wire through an electric field, through a magnetic field, which is the electrical generator, and then goes back and gets heated again as it cools from the turbine. That electric generator is then sending power straight to the grid, and that's what those wires are that you see. So this is the basic idea behind what we hope a fusion power plant would be. And again, a coal or something that burns coal is pretty much this exact same process. It's just the fusion part. It's replaced with burning coal. So hopefully, so this is the basic idea behind what a fusion power plant would look like. And now, finally, we can talk about where are we in the research field in terms of moving towards fusion power plants, and where are we in societies in terms of moving towards fusion power plants. So there are lots of efforts that are currently present to study fusion. Columbia Plasma Physics Laboratory, I'll be talking from the perspective of the Columbia Plasma Physics Laboratory, or the Columbia Fusion Research Center, is one of them. But there are lots of people that we collaborate with, and there's lots of other efforts that are happening around the world. So in Princeton, there's a device called NSTXU. In California, in San Diego, there's a device called D3D. These are both tokamaks. W7X, or Wendelstein 7X, is in Germany, and that is a stellarator. There's devices in South Korea called K-Star. There's a device in the UK called JET that was recently decommissioned. There are many others as well that are not listed here. Here at Columbia, we have a device called HBTP. In the UK, there's also a device called MAST-U. That's a tokamak. There are smaller scale stellarators also at Princeton. One of them is called MUSE, M-U-S-E. There's another stellarator at the University of Wisconsin. There are various other devices around as well. There are lots of devices being built as on top of that. And I'll talk about these in just a second. ITER is one of these devices. ITER is a very big tokamak size-wise being constructed currently in the south of France. It's an international collaboration between many different countries. And it's expected to turn on a bit late in 2034, and it's expected to produce a Q greater than 1, more energy out than in. ITER is not the device that is expected to, the magnetic confinement device that's expected to produce net energy for the first time, as that has not happened yet. Again, the highest Q we've gotten was from JET, was about 0.67. This device was really essential in paving the way to getting different countries interested in investing in fusion, and also having the actual procedure for making a device of this size really ironed out. ITER is a massive device with a major radius from the center to like the center of the plasma, or the center of that donut, about I think it's about 6 meters, which is huge. A person is quite small up next to the side of ITER. So this is one device that is being built. There are some others as well, in the private sector, especially, that are planning on building devices that are supposed to break net energy, or supposed to break Q=1 within the next few years. So one of them is called Commonwealth Fusion Systems, or CFS, which is based in Massachusetts. They're building a tokamak called Spark, which is expected to turn on in 2026. Spark is using high temperature superconducting magnets, which is a technology that allows for much stronger magnetic fields that a lot of fusion devices are planning on using, or that do use. And yeah, Spark is supposed to turn on quite soon, and it's very exciting. We are hoping that it does break net energy. We do work with CFS and Spark here at Columbia, as well as a lot of other companies. Some other companies that exist are Tokamak Energy with the ST40 tokamak. TAE Technologies has their own device. Helion is another company with a slightly different configuration of device. And then there are other companies, General Fusion. Type 1 Energy is a stellarator company. Zap Energy, I mentioned before, is a not necessarily directly magnetic confinement. They have something called a Z-pinch, although it has lots of relations with magnetic confinement fusion. And there are more as well. And there are also plans, in addition, for net energy devices for first power plants. So that company, Commonwealth Fusion Systems, the successor to Spark, is planned to be ARC. The site for ARC has already been chosen in Virginia, and it's planned to be the first power plant to add power to the actual electrical grid, whereas Spark is just a proof of concept, really, to get net energy, or more energy out than in. Demo is ITER's successor. This one is more of a concept right now. We need ITER to work first before this one starts being developed, it seems. So, but this would be the international effort to get a net energy device. And then a bunch of private companies have plans. So Infinity One from Type 1 Energy is there. So first, Type 1 Energy is also producing a stellarator that is hope to produce net energy, more energy out than in. And then after that, their Project Infinity will have. So Infinity One is the net energy device that will first be built, and then Project Infinity is what I think it actually might be called Infinity 2 now, but I should be double checked on that. Is what will be the power plant, or like ARC version of that. And the timeline on that might be a little bit later than ARC, but that is currently in development as well. In addition, there are some other devices for other types of power plants. WHAM from the University of Wisconsin is a magnetic mirror device, which is another type of magnetic confinement fusion we haven't talked about much, but it's another concept. And it's kind of coming out of Rialta Fusion. This one, again, the timeline's not as clear, but it's also in development. EOS from Theia Energy is another stellarator that, instead of using large coils, uses very small but lots of coils. And we might talk more about a concept like that later in this course. These coils are the electromagnetic coils that create the magnetic fields needed. This is another power plant concept that is, again, under development. Timeline is not as clear, probably a bit later than ARC and Spark. There's much more funding in the tokamak realm at this point than there is in the stellarator realm, although in private industry, many companies are being quite well funded on both sides of stellarators and tokamaks. thanks to the private industry funding sector, whether that's venture capitalists or something similar or private investors. So that's very exciting. And these graphs that I'd like to show, so this is pretty indicative of like how far we're coming with fusion. So this is a graph of on the horizontal axis is how hot the devices we're creating are getting, what the triple product is on the y-axis, and then the y-axis is also directly correlated with the time that these devices have been created at. So you can kind of see over the last, there's a pretty clear trend here of in the 70s, 80s, and 90s, as we were driving up towards Q equals 1 in this graph, looking at like a linear slope as the, although we're on a log scale or an exponential scale on the triple product. So we're getting quite close, although there was still like getting the barrier to getting to Q equals 1 is pretty tough. And we obviously haven't broken that yet, but from going all the way down like to lower and lower Q, we've come quite far. And a little bit more complicated graph. Yeah, sorry. So there was actually a mistake on the last slide. There was a world record of 22 minutes recently set in France for fusion plasma in a tokamak. That was very impressive, but actually wasn't a super high triple product. If we're looking at triple product as our fusion power metric, which is I'd say the better fusion performance metric to look at, especially than just simply time, because it takes into account temperature and density as well. The devices that have been created are so first of all, that 22-minute shot wasn't a very high, or the 22-minute plasma was not a very high triple product. However, looking at this graph, we can kind of see the trend of where devices are moving. This is still on a log scale, but this is with more devices. So you can see ITER and Spark in the top corner above, in the top right corner above Q equals 1. You can see NIF having gotten above Q equals 1. And then you can see how close some of these devices are coming to this Q equals 1 line that is up in the top right corner. You can also see the separation between stellarators and tokamaks. So JET, TFTR, D3D, these are all tokamaks. And then W7X is not a tokamak. W7X is a stellarator. And now in stellarators, the rule of thumb currently is that stellarators have been about an order of magnitude below tokamaks in triple product, and that's currently where they sit at today. Although stellarators have a very promising future, they have not had the funding to produce as many devices as tokamaks have. Hopefully they will produce more in the future. And finally, just a little bit about the Columbia Plasma Physics Laboratory. And actually, I guess before I say about the Columbia Plasma Physics Lab, these trends are, they're very promising. It's definitely a barrier to get over Q equals 1, but our devices and our projections for these new devices, Spark and ITER, with the plasma physics and fusion physics that we know right now, do have these devices going over a Q of 1. These are very real simulations. We're building them so they go over a Q of 1. And hopefully within the next few years from when this video is created, we'll have a net energy Q is greater than 1 magnetic confinement fusion device. I'm very hopeful. And at the Columbia Plasma Physics Lab, a lab that was established in the 60s, we have a tokamak, HBT-EP, one of 3 currently operating in this is the US in this country. We also have a stellarator that's currently being upgraded to CNT to CSX that has 2 interlock coils and creates a plasma that goes kind of in this donut shape, but it's got a kind of a funky shape in it. We're getting a new tokamak that's currently being assembled that's called Q, the Columbia Undergraduate Training Experiment, or tokamak experiment. I'm not sure that name has been solidified yet. We also collaborate with lots of national and international people, CFS, General Atomics, Princeton. A lot of really awesome stuff happens here. We do a lot of fusion, a lot of plasma. I wanted to put this here, some cool visualizations of tokamaks and stellarators. If you're interested, take these links. You can kind of look around these devices and get a sense of what goes into them. And we'll talk about a lot of the components throughout the next few classes. And yeah, to summarize, we're making great progress towards fusion energy. There's still a lot left to learn about plasmas and fusion. There's still a lot left to do. I encourage you to remember the 3 types of Q values and remember what Q is when you're thinking about different fusion achievements or fusion news that you're hearing about, or analyzing different devices and developments in the fusion community. Thinking about triple products as well when you hear these announcements. It's a really good way to contextualize and measure progress and be realistic about what's happening with these devices. And get involved. So this is just the beginning. This is just the foundation. We've now pretty much concluded the basic knowledge behind what the motivations behind fusion energy are in the fusion energy magnetic confinement field, which, again, the magnetic confinement device type is what is mainly used for energy production with fusion. And yeah, we've now learned the basics. We've learned the basics of plasma. We've learned the basics of fusion and creating fusion devices, tokamaks, and stellarators. And in the next few courses, in the next few videos, we're going to dive in with more detail to the actual physics that goes behind these plasmas, and then the actual building and analyzation of and different types of these devices that I've talked about in the past few videos. So I hope you had fun in these videos. I hope you learned a bit. Feel free to visit the Columbia Plasma Physics Lab website, learn a bit more about us. Again, contact us if you have questions. Put questions in the chat, and we'll do our best to respond to some of them. And start conducting plasma infusion research yourself. I hope that these videos have sparked some interest in the fusion field and in the plasma field. There's a ton of great opportunities, whether you're a high schooler or a college student, an undergrad, and you're thinking about, in either scenario, doing fusion. If you're in the US or if you're out of the US, there's many opportunities around the world for this. I've linked some opportunities that we have posted on our website for the Columbia Plasma Physics Laboratory that reaches the opportunities that we're aware of that are around the world and around the US as well for high schoolers and undergrads and just other students on the website that I've put at the bottom of this slide here. So please feel free to, and I encourage you, apply. You never know when you'll get a position and then you suddenly start a career in a field like this. And this is certainly an amazing and exciting field to be a part of. It's very quickly developing, and it's super exciting all the time. There's also really great people in this field, and just the work is like super, super interesting and rewarding. So I hope you enjoyed. Thanks for tuning in, and we'll see you next time. Bye.